In this question, the photograph shows an exercise device and someone using it. The device contains two rubber cords which are extended when the device is used. A student investigates the property of device by hanging a weight on and measuring how much it has extended. The student obtained this graph, a force and extension graph. The student noticed that her graphs is a straight line between A and B and conclude that the device obeys Hooke's law. So what is the Hooke's law? Hooke's law state that there should be a straight line which is passing through origin. Like force, Hooke's law simply state that force and extension are directly proportional to each other, and the graph between the two quantities, it should be a straight line which is passing through origin. So student is saying that in region AB, like straight line between AB, it's the device is obeying a Hooke's law. But it's not like it should only be a straight line. The condition is that it should be a straight line, but from the origin. If it was from AB was from the origin, starting from origin, it was a straight line. That case, we will say it was obeying a Hooke's law. But here, as it's not a straight line, it is a straight line between A and B, but not starting from origin. So we say it does not obey the Hooke's law. So the Hooke's law states force and extension directly proportional. And when two quantities are directly proportional, there should always be a straight line which is passing through the origin. Describe how the student could use a graph to obtain an estimate the total work done. How we calculate a total work done? Work done is basically calculated by area under the graph for force and extension. Because how we know that the area under the graph will give us the work done? Because when you take a slope of the quantity, slope of the graph, slope is a quantity on y-axis divided by quantity on x-axis. So the quantity on y-axis is force and on x-axis is extension. So it does not give, because to give a work, we should have either Newton meter or Newton centimeter, because the unit of the work done is joules. So it should be Newton meter, means force into distance, not force divided by distance. So if I take a slope, the slope will not give us the work done, as it is the quantity on y divided by x is not Newton into meter, it's Newton divided by meter. But when we take area under the graph, area under any graph give us the quantity on y-axis multiplied by quantity on x-axis. So here, y-axis we have Newton, on x-axis we'll have centimeter. We can convert into meter, so Newton centimeter or Newton meter. So Newton meter will be joules. That's how it will give us. So what we have to do to calculate the work done, we have to take the area under this graph. So the distribution, like, and it's a non-linear graph. So one mark you'll mention, find the area under the graph. And second thing, you can divide into small squares or regular figures and then count the total number of figures, because it's a non-linear graph. If it was a linear graph, you could use a specific, like if it was a triangle, half base into height. If it's a rectangle, length into width, or trapezium, it will be sum of the parallel sides into height. So one mark for mentioning finding the area, and then second mark how you will do or calculate the area, as it's a non-linear graph. So for non-linear graph, what we usually do, we divide into equal, first we draw equal horizontal lines. And equal vertical lines. As it's a non-linear graph. And then we count the number of the squares, number of the boxes. If it is, first we count for a complete one. And then we check whether it's half, like two combined. So this will be 1, 2, 3, 4, like this. We count the total and area of each box. Area of each box number multiplied by number of the boxes. You get the total area. And that will be equal to the work done. The next, the student sets up a spreadsheet to investigate the work done in stretching the device each time. The weight is added. You can see like work done is force into distance. So initially, like we apply a 10 Newton force, extension was 1.6. How much has changed? And then we calculate a work done, which is force into distance. But because the work done should be in joules, so that's why distance, the extension which was there in centimeter was converted into meter first. So how we calculated, we just take a difference. Like it was 1.6, then how much is the difference? It was like 1.9 centimeter, but we convert into meter, and then force into distance, we calculate a work done. This is a spreadsheet to calculate the work done. Then the next part, explain why the spreadsheet results is overestimation of a total work done. What is the reason for that? Like, why it's an overestimation? The reason is that, as you can see the difference between the force. Like every time we are changing a force by 10. So maybe, like example, say when a 10 changes to 18, it might have the same extension. When 40 changes to say 47, it might have the same extension as 40 changes to 50. Because like a small change in the, so what we should do, we should have a small change in the force here because there's a large change in force, so the extension might not be correct. Like we may have the same extension at 49 and 50, or they're very close to each other. So as a result, the force which we are using is much higher than what actual force is. So when we calculate a work done is force into distance. If this distance might be same for like a force of 49 Newton and 50 Newton. So if the force which we are applying is more, the work done when we calculate, it will be very high. That's why it's an overestimation. So why it is overestimation? Because of the force, the change in the force, as there's a greater gap or difference between the force, change in the force, it might result in overestimation. So we use the maximum amount of force each time. It should be like small changes in the force should be there, so we can work out the work done correctly. A student, a student eats a packet of crisps and then use the exercise device. The energy content in a packet of a crisp is 540 kilojoules. During exercise, this energy is converted and 25% of energy is transferred into mechanical work. Like remaining 75% of the energy is wasted in the form of heat. The student extends the device fully 15 times in 1 minute. An accurate value for a work done for fully extended device is 14.7. Like when the device is fully extended, 14.7 joules of energy is used. Calculate the time it would take the student if he's working at this rate or the power to transfer 25% of energy from the crisp into mechanical work. Like how much 25% of this energy, if he's using 25% of this energy, how much time he will take to do this? That is the question. Like how much time he will take to consume 25% of 540 joules to do the exercise. And when he's doing, like he extend in 1 minute, he's extending 15 times and using 14.7 joules of energy. So first we'll calculate the 25% of this 540 kilojoule, and then we'll find how many times he stretches. Like one time stretch, when an accurate value for a work done is for the device, like one time it is 14.7 joules of energy. A student so Using that, we'll find how many times he did this stretch. And then if 15 times in 1 minute, then we'll find number of stretch in how many minutes. So I'll solve this. So first, we'll find 25% of 540. It's a kilojoule, so don't forget to convert the unit. So 540 kJ means 540,000 joules. So we'll find 25% of the 540,000. Because efficiency is you can use a formula for efficiency, or you can use just your understanding, like 25% of the total energy. So it will be 25, because to convert the percentage into fractions, so it will be 25 divided by 100. So this will be, he used 135,000 joules of energy. That's the first thing. Then when he did like how many times he stretches, one time he consumed 14.7. So to use this much energy, 135,000, how many times he should stretch? So the total energy is 135,000 divided by each time he used 14.7. So how many times he stretches the device? 9,184 times he stretches the device. Then if he do 15 stretches, if he's 15 times, he did in 1 minute. So if we want to find 9,184 times, how many minutes he will take X? Just cross multiply. So it will be 9,184 divided by 15 is equals to X. So when you divide, it will be about 612 minutes. So he will take about 612 minutes to completely transform this energy. Is it clear, this example? Yes, you can write the answers in second. The SI unit of a time is second, so it's fine. You write the answer in second. So the main question was like how much time he will take to consume 25% of the energy from the food to do this exercise. So what we did, we work out what is the 25% of the total energy he's using. Then when he use energy one time, like 14.7 joules of energy is used for one time. So we find how many times he did this stretch for the exercise. And when 15 times he's taking like 1 minute to do, then 9,184, he will take X, then we'll get the answer in minute. You can write the final answer in second as well, that's fine. Explain whether more or less work would be done applying the same maximum stretching force for a similar exercise divided with a rubber cord twice the cross-sectional area. So as I mentioned, the work done depends on the force and the distance moved. So if we have a like large cross-sectional area, because thinner cords, thinner rubbers are easy to stretch as compared to thick. So the thick one will have a small extension as compared to the thin one. So as a result, when we calculate a work done, which is force into distance, we are applying the same force, same maximum stretching force. But for the rubber cords, when they're thick, as a result, it will be like stretching will be less. So if we apply the same force, but stretching is less, as a result, smaller or less work will be done. As the work done depends on the force which we applied and the distance moved. So these are the questions from exercise work, energy, and power.